Vectors, you guys, a lot of quantities in physics are represented by vectors, like velocity of an aircraft. So the length, how long the arrow is showing like how fast it is. You know, if you speed up, you would lengthen the arrow. And then the direction of the aircraft is obviously represented by the direction of the arrow. So that would be like a velocity vector. And a vector is a quantity that has both magnitude and direction. And unfortunately, I can't show you. I'm always excited to show my vector villain video, so I'll have to reference you this clip. But I love this clip because he's introduced to a vector, and he keeps saying how he has both magnitude and direction. So anyways, you'll have to look at that if you remember that from Despicable Me, the vector villain clip. So that's what I want you to remember, is that vectors have both magnitude and direction. They have both magnitude and direction. So if a vector has the same direction and the same magnitude or length, like here, see how I'm going up 3, 1, 2, 3, and then right 4. This one also goes up 3, right 4. This one also goes up 3, right 4. So they have the same slope, they have the same direction, and they have the same length. The length of that ray or that arrow is the same. So these are all equivalent vectors, even though they're at different spots. They're equivalent vectors. You can add vectors, and when you add vectors, what you do is you take the starting point of the first vector. So see how this vector v goes up 1 and right 4, and then vector w goes up 3, right 3. So v plus w will go from the beginning part of the v to the terminal point of w. So v plus w is right there in red. That's how you add vectors, okay? And the commutative property of addition holds for vectors. So in other words, vector v plus vector w is the same as vector w plus vector v. So here it's showing v plus w is right there. But if I did w first over here, so I went up 3, right 2, and then I did v second, it's still the same vector in the middle, right? W plus v. So the commutative property of addition holds, and also the associative property holds. So if you do v plus w first before you add it to u, you could also, it's the same as u plus v plus w. So the associative property holds also for vectors as well. Now, what about a negative vector? So it's drawn as the same as the original. So the length is the same, or the magnitude, or the length is the same, but it goes in the opposite direction. So notice v here goes up 3, right 1, 2, 3, 4, up 3, right 4. So negative v would just go down 3, left 4. See how it's down 3, left 4? It's just going in the opposite direction. That's all that the negative does. And so if you're doing like v minus w, what you do is you actually just go v plus, and then you go in the opposite direction of w. That's how you work with adding and subtracting. And we'll do some examples here. So let's do this first one. Here's our vector v, vector w, and vector u, okay? And the first one we're going to do v minus vector v minus vector w. And so we'll go vector v plus, and then we'll go in the opposite direction of w. So let's do vector v. So notice vector v here. See how it goes up to, let me do it in blue, up to right 3, right? And that's vector v. So let me come over here and let's go just start right here and let's go up 2 and right 3. And let's draw vector v. Okay, here's vector v. Plus, now let's do minus w, right? The opposite of w. So instead of going down 2, right 2, I'm going to go the opposite direction. I'm going to go up 2, left 2. That would be, this would be negative w, vector w. So up 2, left 2. So I'm going from here, but I'm going up 2, left 2, and I'm going to draw that right there. Erase this other stuff. Okay. So up 2, left 2. Okay, so let me label this. This is vector v. That's the opposite of vector w, the opposite direction. So our solution, v minus w, or v plus negative w, goes from here, the starting point, to the ending point. So that's our vector that we want. V, that's the resultant vector in red. Any questions about that? It's 2v, so double the length of v plus triple the length of w. So notice v goes up to right 3. So I'll do that twice. 2v plus 3w. Go up to, let me start. Up to right 3, but I got to do it twice. Up to right 3. Okay, here's double v. 2 times vector v. Now, so that's 2v. Now I'm going to add on 3w. So let me look up here at w again. See how w was down to right 2? So I want to do that, but I want to do it 3 times. Down to right 2. Whoops, let me erase that. Down to right 2, but I got to do it 3 times. Down to right, so I'm starting here, and I'm going down to right 2. Down to right 2, down to right 2. So I did that 3 times, because that's 3. The magnitude is increased, tripled it, right? 3 times w. So the resultant vector, remember we're adding 2v plus 3w, is I started here and I ended here. So there's my 2 vector v plus 3 vector w. That's my resultant vector in red. Any issues on that, you guys? Let me start about right here. 2v, so our v was up to right 3, so I'll double that. Up to right 3. Is that right? Yeah, up to right 3. Up to right 3, cancel. Okay, so here's my 2v. And then minus w, so I've done this one. And then minus w, remember w was down to right 2. W was down to right 2, but I want to go the other way, so up to left 2. Up to left 2. Okay, so there's minus w. And then plus u. Let's go look at u. U was up 3, right 1. So up 3, right 1, again from here. So here to here. And so the resultant vector started here, ended there. So I want to draw it from there to there. In red. That's 2v minus w plus u. Okay. Horizontal component and the vertical component. So vector v can be expressed as AB there, horizontal and vertical components. And this is the position vector is where it's showing, you know, because you can have multiple vectors all over the place and they could be equivalent. But only this one's the position vector because it starts at the origin. So even though these are equivalent vectors, they both go up 2, right, 3, they have the same length and direction. The position vector is the one that starts at the origin, okay? And the algebraic vector here is saying that if you were to draw it, that's giving you the coordinates from the origin, the position vector. So let's do this first example here. Find the position vector if you have 2 points, -1, 2, and 4. 1, 2, 3, 4. Okay, here's the original vector from point 1 to point 2, right? Here's x1, y1, here's x2, y2. If you were to find your position vector, then we're going to use this right here. The position vector, v we'll call it, is x2 minus x1, y2 minus y1. And so x2 is 4, right? So I have 4 minus a -1, comma, and then the y2 is 6 minus 2. So the position vector, 4 plus 1, I got 5, comma, 4. Here's my position vector v. Well, if I plot 5, 4, 1, 2, 3, 4, 5, 1, 2. Can you see how there's my position vector that starts at the origin and then hits that spot of 5, 4. So these are equivalent vectors, but that one's the position vector displayed there on the graph, okay? Why don't you guys do y2, our position vector. It is 6 minus a -1, comma, -2 minus that 4. So we've got 6 plus 1, -2 minus 4, 7, -6. As you guys mentioned, there's our position vector. All right, for this next one now, what if we're given an R vector, an S vector, a W vector? Can we find the resultant vector here, 3R minus W plus S? Well, let's substitute in our vectors. 3R, there's our R vector, minus, and then we got W plus S. Well, we'll take the 3 times each of those, so we'll have 6, 3 times 2, and then 3 times 5, I'll have 15. Oops, 15. Minus, and then in here, what I do is I take the W plus S, so I get W plus the same term over there, -2 plus -2, we get -4. And then I'll take the 5, the Y, plus the -3. 5 plus -3 at 2. There's W plus S. And now I'm going to take the 3R minus the W plus S. So I'm going to go 6 minus a -4. Again, 6 minus a -4. And then I'm going to go 15 minus the 2. So we got 10, comma, 13 is our resultant vector here. Okay. Now there is another way to do this algebraically, and that's to put it in its alternative representation of a vector. And so if I let I hat be the unit vector 1, 0, that's its horizontal component, and I let j hat be 0, 1, the unit vector in the vertical direction, then if I have the vector v being a, the horizontal component, b being the vertical component, I can express this as a times the horizontal component plus b times the vertical component. In other words, a I hat plus b j hat. That's another way to express AB. Okay, so this is your alternative form. That's just I just want to give you a little bit of background on that. So if you're doing that same problem above, you could put it in terms of I's and J's, and we'll do that. We'll do that here in a couple examples. So give me a minute. All right, now what about its magnitude or its length? Right, if you're finding the length, you know, and you have of the vector v, right? Well, a is your horizontal component, b is your vertical component. You know, a squared plus b squared equals v squared. So the magnitude of vector v is just the Pythagorean theorem if you solve for that length of v, right? So don't forget the magnitude of a vector. So let's say we have 6i plus 3j. There's vector v. So what's its magnitude? Well, here's my a and here's my b, right? I went over 6 and I went up 3. Oops, 3. So the magnitude square root of a squared plus b squared. We get 36 plus 9, what's that, 45? 9 times 5, square root of 9 is 3. So the length of this vector v is like 6 point something units, right? That's that length of vector v, magnitude of vector v. All right, now let's work with these alternative forms. You see how you have this vector v here is a position vector. See how it's a 1i plus 2j. So this is 1, 2. That's the other way to represent this. This vector w, we're writing it again in the alternative form, but it's -3, 4. That's the position vector. But what we're going to do, it's easier to work with it algebraically, is we're just going to go -2v plus 3w. So I got -2, v is 1i plus 2j plus 3w. Well, my w is -3i plus 4j. It's just nicer to work with it algebraically with these variables i and j, I think. -2i minus 9i, I got -11i, -4j plus 12j is plus 8j. -11i plus 8j is the resultant factor, or -11, 8, same thing. The resultant vector. Okay. V minus 4w. This is a good time. Why don't you guys go ahead and pause it and try this next one. V minus 4w. Given is -3i plus 4. Oops. It's an I plus 4j. I plus 12i, 13i, 2j minus 16j negative 14j. So 13I minus 14j, or 13 negative 14 as our result vector there. All right, how about the magnitude of v plus w? So v plus w, first we gotta find v plus w first, right? What is v plus w? V plus w, what is that first of all? And then we'll address the magnitude of that. Well, the v is I plus 2j, and the w is negative 3i plus 4j. So I minus 3, I got negative 2i. 2j plus 4j, I got 6j. So negative 2i plus 6j. So my a is negative 2, my b is 6. Right? And so when I'm finding my magnitude of this, squared a squared plus b squared. So I got negative 2 is my a, 4 is my j. We got 4 plus 16, I got square root of 20. Well, that's oh, I'm sorry, gosh, I just realized that is a 6 right there. I'm sorry, that was a 6. That's 6. Grief. I got 36 plus 4. I got square root of 4. There we go. Square root of 40, which is what, 4 times 10, or 2 root 10. So it's like 6 point something, right? So the magnitude of vector v plus w is 6 point something, 2 root 10. Any questions on the magnitude of vector v? Its length, its magnitude. And that'll give you a unit vector. So for example, this one, 12i plus 5j, 1, 2, 3, 4, 12. Okay, so here's vector v originally. And what we're looking for is we're looking for the unit vector. So it goes in the same direction, but it's only 1 unit in length in red. It's only 1 unit in length, but it's in the same direction. And so what you want to do is to find the unit vector, you take the original vector and you divide it by that vector's magnitude. So number 1, let's go ahead and find the magnitude of vector v. Here's vector v, 12i plus 5j. So my a is 12 and my b is 5. So if I'm finding the magnitude, let's throw it in. So 144 is 25, 169, square root of 169 is 13. Okay, so we know the length or magnitude of vector v is 13. And so we'll go ahead and now number 2, let's find the unit vector. So the unit vector is vector v, 12i plus 5j, but I divide it all by its length, 13. Well, that's a common denominator, so I got 12 13ths I plus 5 13ths j, or 12 13ths, 5 13ths, right? So it goes to the right 12 13ths and then up 5 13ths, and that's that vector u. If I could blow that up, right? That's that vector u right there that only has a length of 1. That's a unit vector, length of 1. This one, once you guys try this problem, do the same thing. See if you can come up with the magnitude of vector v. Notice the a is negative 2, the b is 3. We got 4 plus 9. I got square root of 13. So 3 point something, right, is my magnitude or length of vector v. So in order to find The unit vector, which goes in the same direction, but it's not as long, is I take the original vector and I divide it by its magnitude. Well, the original vector is negative 2i plus 3j, but I got to divide it by the square root of 13, the magnitude that we just found. And so the unit vector is negative 2 over root 13i plus 3 over root 13j. I do want to rationalize that. Let's multiply by root 13. Same thing here. We'll be proper about it and rationalize it. So vector u is negative 2 root 13 over 13i plus 3 root 13 over 13j. And there's our unit vector for that one. All right, vector components. So a vector is made up of both a horizontal and a vertical components or parts, right? And so this picture is showing us just how to break this up into the components. And we're going to use this formula to do that. So the vector v is the magnitude times the cosine of its angle. That angle alpha is the angle between the x-axis and the vector that we're going in the direction of for vector v, plus the magnitude times the sine of alpha j. Okay, so we want to highlight that. So we'll use that. So let's write this vector here in terms of I and j. So if we're given the magnitude and we're given this direction, alpha being 30-degree direction, let's go ahead and write vector v in terms of I and j, given those two, that information, right? So vector v equals the magnitude, which is 8 cosine of alpha I, plus the magnitude 8 sine of alpha j. And so we got the cosine of 30 degrees is root 3 over 2. We get the sine of 30 degrees a half. And so we got 4 root 3i plus 4j, and that's vector e, given magnitude and that angle, 30 degrees, right? Now the resultant vector is just the result when you add the two vectors together. That's the resultant vector. The direction of the resultant vector can be found. You can find theta by taking the arctangent of b over a. We'll talk about this. If it's in quadrant 1 or 4, you can leave it alone. If it's in quadrant 2 or 3, because of the arctangent restrictions, you got to add 180 degrees. And that's because it's spitting out a different angle due to the inverse tangent, okay? Now, static equilibrium, that's when the sum of all forces is 0, which means nothing is moving. So the magnitude and direction will both be 0 on that. As again, just some more vocabulary. And I should also throw in, you know, a velocity vector is like a vector, like an airplane, where you have speed and direction. The speed notated by the length of the arrow. A force vector, on the other hand, is a vector that represents direction as well, but the amount of force that's acting on the object. So the more the force that you have, the longer the arrow or the ray. And so here's an example where you've got a force vector. You got two forces of magnitude. The first one is 30 newtons. Notice the 30 Newton one right here, which has a shorter arrow than the 70 Newton one, right? Longer, more magnitude, more force. The first one has a 45-degree angle. You can see the second one's got a 120-degree angle. Find the direction and magnitude of the resultant force. Well, number one, we need to break this up into components. So for the first one, remember, it was magnitude. It has a magnitude of 30, magnitude, and then it's cosine of its angle, 45 degrees I, plus magnitude again indicating length, and then it was sine of 45j. Okay. And so this ends up being, so I'd go ahead and punch in 30 times root 2 over 2. I get 21.21 I, and I can do I hat if you want to indicate it with a hat. Sometimes I get lazy and don't put my hats on. 30 times sine of 45 degrees, 21.21. Okay. Okay. There's the first one. Let's do the second one. Now it has a magnitude of 70 newtons. 70 is its magnitude. Cosine, this time it's a 120 degree angle, it said. 70 sine of 120 degree. Again, make sure your calculator's in degree. So the second vector is negative 35 I plus 60.62 J. Okay. Now we can add them. So let's add and find the resultant vector. So step number 2, F1 plus F2 would be. So I got 21.21 I plus 21.21J plus negative 35 I plus 60.62J. So let's combine the I's. Let's combine the J's. And I get negative 13.79 I plus 81.83 J. Okay. There's our resultant vector. Step number 3, let's find the magnitude now. So the magnitude of this resultant vector. Well, that would be the square root of a squared, there's the negative 13.79 squared, plus b squared, that 81.83 squared from the resultant vector. And that ends up being 82.98 when I run the square root on that. That's our magnitude. It's the length of the resultant vector. Okay. The resultant force, if you will. All right, now how to find the direction of this resultant force. So what we're going to do, find the direction, is we're going to go ahead, and I should say, let me note for a minute, let me highlight this. Here's the resultant vector, right? Negative 13, if I was drawing it, negative 13.79, 81.83J, and it's like, I don't know, it's like way out there, right? It has a really, the magnitude's 82.98, right? So it's into quadrant 2, right? My negative 13.79, and I'm up 81.83, but it's really long. Magnitude's 82.98, it's our resultant force, okay? So how do we find that angle, theta? Well, what we do is, let's say I was drawing this, right? This is negative 13.79. This is 81.83, right? So here's my A, here's my B, and I'm trying to find theta, but I'm using right triangle trig to do this. So I have the tangent of theta using theta prime, I know, is opposite over adjacent. And so the theta will end up being the arctangent of this. Now the problem with this is when I'm taking the arctangent, remember when we cut off the arctangent, we're always looking between negative pi halves and pi halves. So it's spitting out a theta. Let's see what this thing spits out. pull up my Desmos. And I wanted to spit out in degrees, so I make sure I'm in degrees. Let me take the arc tangent, and I had 81.83 divided by negative 13.79, I believe it was. Oops. There we go. So negative 80.43. I go back. So it's giving me this angle, right? It's giving me, oops, negative 80.43, but we want the one over here. So we got to add 180 degrees to that. So because this is in quadrant 2. So degrees plus 180 degrees. So theta here ends up being 99.57 degrees. I posted there in the notes is if you're in quadrant 2 or 3, make sure you add 180 degrees to that. Otherwise, you're okay. You just take the arc tangent of B over A. Okay. So the next part of this, flip this back over, pull my pen out again. The last part of this question says, after we found the magnitude, right? We found the direction, and that's telling us that this is right there. That's 99.57 degree. That's that direction of this thing. We also find what additional forces need the object to be in a static equilibrium state. Well, in static equilibrium, all the forces need to add to 0. And so here is our resultant force, right? But we need the forces to add to 0. So we essentially need it to be 0. So we would need a positive 13.79 and a negative 81.83. And that's the additional force needed. So you just switch those so that when you add them, they go to 0I, 0J. Right? That would be the force necessary. The force necessary would be the opposite of that resultant force. Okay? So the result would be 0 for both vector components. All right, let's do another one here. The magnitude and direction exerted by tugboats towing a ship are 42 north, 65. So off of north on 65. Oops, is that not drawn? Degrees east, and I'm doing this for 100 pounds. The next force is 8 degrees. So off of the south, 58 degrees east. $3,000, so a lesser force. £3,000. Now we need to break this up into components, but notice the degree that we actually want is right there. So 65 minus 90, that'd be 25 degrees. This one down here, 58 minus 90 is a negative 32 degrees on that. And so that's number one. Let's find the actual angles that we wanted. And now let's go into let's write our vector. Let's write it with the horizontal vertical components times cosine of the angle I plus its magnitude of the vector sine of the angle I for the first one. And it has a magnitude of 4,200 pounds. The angle is 25 degrees. And 4,200 pounds, angles 25 degrees. Oops, that's a J. 4,200 times cosine 25 degrees. Make sure you're in degrees. That'll give you 3806.49. 4,200 times sine 25, I get 1774. Gosh. 0.99. Okay, there's vector. Now let's do the second one. So this time it's 3,000 pounds, and it's the cosine of that negative 32 degrees plus 3,000 sine negative 32 degrees. And so multiply those, we get 2544.14 pi. And then 3,000 times sine negative 32, that's a negative 1589.76 J. For the second vector there. 3, we want the resultant force. So we want both the magnitude and the bearing of the resultant force. Well, let's find the resultant. All right, so step 1, step 2. Ends up being, so I'll take the 3806.49 plus 2544.14. I get, let's see, that's 6350.63 I. Again, I'm adding that force 1 and force 2 vectors together. Get 185.23. Okay, so there's the resultant vector. Add those two together. Now let's find its magnitude. So square root of A, 6350.63 square root of A squared plus B squared. And this will end up being 6353.33 pounds. So that's the length of the resultant vector. And then now let's go ahead and find the direction. So step 4, direction. I'm going off of, here's my resultant vector. So my A is 6350, my B is 185.23. So if I'm drawing this thing, I'm going right 6350, and then I'm going up a little bit. So the resultant vectors there, right? But the way you find that, you say, well, I went to the right, 6350.63, that's my A, and then I went up 185.23, that's my vertical component B. So the tangent of theta would be 185.23 over 6350.63. So I take the arc tangent of that. Make sure you're in degrees, so it spits it out in degrees. And you get your theta being 1.67. Now, again, this is, if it's in quadrant 1 or 4, you're fine. You don't have to add 180 degrees, right? So this is measured from the x-axis, right? So right here, this is the 1.67 degrees right there. Now, what we want is we actually want the bearing. So we got to do a little bit more to this. We want the bearing north, such and such degrees. I'll call it alpha degrees east, right? We want north, alpha degrees east. Well, if theta is 1.67 degrees, then 90 alpha would be 90 minus 1.67 degrees. So my alpha here would be 88.3 degrees. So our bearing is north, 88.3 degrees east on this. Any questions on that one? On here we've got 3-pound pictures hung from a wire, from 2 wires as shown below. The tension on A is 3.4 pounds. That's your magnitude, right? At 161 degrees, tension on B is 9.2. That's why it's longer, right? More pounds, more force on that. At 69.55, the tension on C. So let's go ahead and put it in component form. So for A, let's see, tension on A is 3.4 pounds. So magnitude, cosine, 161 degrees. There's our component, magnitude, sine of its angle. There's its vertical component, which is now let's do it for B. B, we've got 9.2 pounds, more magnitude, its cosine, so here's its angle, 9.2 sine, 69.55 degrees J. So we got 3.21 I plus 8.62 J. Now let's do C. Tension on C is 9.73 pounds. Cosine negative 90. I. 9.73 pounds sine negative 90. So I got cosine negative, so I got 0 I. Sine negative 90 is just negative 1, so I got minus 9.73 J. Here's step 1. Step 2, find the direction of the resultant force. Well, if we add A, B, and C, add all these together, negative 3.21 plus 3.21 plus 0, we get 0 is your horizontal component, and then 1.11 plus 8.62, that's 9.73. Guess what? 0 J. So this means the magnitude and direction are all 0. Therefore, we have a state where the vectors are in static equilibrium. And thanks so much for watching. I hope that. Thanks for taking notes. See you next time.